Hi, my name is Vincent, and today I'm going to talk about Physics 2211, which the first lab talks about constant velocity. And in the introduction, in my presentation, I'll talk about the purpose of this lab, and then I'll tell you about the steps inside my experiment and how data is used. And later, I'll compare and plot these two models together, and I'll answer some further questions. So the purpose of this lab is to do experiment and observe the position of an object moving with the same speed and no direction change. In this experiment, I'll use the battery as a rolling object on the flat surface, and I'll use tracker to observe and track data of the position of my object, and later I'll use Glowscript to graph the predicted position of the object. This experiment will demonstrate the principles of Newton's second law, which will be introduced in the following slides. So to begin with, I'll talk about the Newton's first law, which states that an object remains at rest or in motion at a constant speed in straight line, except being acted upon by an unbalanced force. So this is highly related to the Newton's second law, which states that at any time the net force on the body is equivalent to the rate at which the body is momentum. When you take the integral of both sides, you'll see that m multiplied by final velocity minus initial velocity equals to s multiplied by final time minus initial time, and you'll get the updated velocity equation. So you can see that if the force acting on the object is zero, the velocity is constant over time. So I'm going to talk about the brief preview of the main results of the lab. In overall, like the red line represents the computational position, like the predicted one of the object over time. And my blue graph represents the experimental position of the object over time. You can see that the blue graph is linear, indicating an approximately constant velocity. And these two graphs are pretty close together, which I'll discuss later. Steps inside my experiment is to record a video of the battery rolling on a flat surface at a constant speed, and I'll use tracker to track the battery position over a set time period. And later I'll use Glowscript to create a model of the battery predicted motion, and then I'll sketch a graph to see the comparison. So this is the video of my experiment. So you can see that this is the tracker data that I have screenshot, and then to begin with, I start with the time at 0.367, and then there's a time interval of 1 divided by 30 seconds. So you can see that the graph is pretty linear, indicating like I say, a constant velocity over time and a approximately zero net force acting up upon on the object. So yeah, because we assume that the F net is equal to zero, the mass to the object is not very important. So the ball position is where I start is 0.002729, and then it's the initial position of the object. I track my start time is 0.367, and then between then I have a difference time is 1 divided by 30, and then the difference in position is delta x. So I can calculate the initial velocity, which you can see on the left hand, which is about 1.64. So when I sketch this, I got a data of the time from like 0.3 seconds to 1.2 seconds. And then I'll get the updated position every time. So when I compare these two, I see that they start at the same position, and they have a small difference between these two graphs. And you can see that the blue graph is pretty linear, indicating like a constant velocity, approximately constant velocity, and approximately zero net force acted upon the object. And these two are pretty close together, meaning that I think I have nailed the experiment. So the errors that may possibly happen leads to differentiation in the model is the frictions of the flat surface or the error system not calculated to make the force unbalanced, or maybe a rounding error that leads to numerical error, or maybe an error while I identify the center of the mass of the object during tracker. So I'll talk about like I will answer some further questions. So how the results would change if I will flip the axis. Like I think that the x or y coordinate axis will rotate, resulting in a negative slope of the graph. And then is it possible for me to say that how many pushes and pulls or how many forces or added to give zero net force in the case that I observe? I think that the computational model overestimates at a greater time, like only a little bit. So there should be an unbalanced force acting on the object. So my assumption of the F net equals to zero is not accurately. It is just like I think that it's just approximately equal to zero, and the velocity of my object is approximately constant. So thank you for your listening to my presentation. I hope I can see you guys in the future.